start with our next revision, the second part of the linear motion, which is the linear motion graphs. So basically, linear motion graph can help us describe the whole journey of the motion of the object. So there are three types of motion graph, linear motion graph. The first one is the displacement time graph. Next is the velocity time graph, and lastly is the acceleration time graph. So basically, the most important type of linear motion graph is the velocity time graph because it has a lot of information. Plus, it contains the information about the acceleration and also the displacement of an object. So the velocity time graph actually is the most completed description of motion for an object. But it doesn't mean that the displacement time graph and also the acceleration time graph is not important. We also use sometimes the displacement time graph because it's easier to integrate the movement of an object relatively to the position of displacement. Whereas the acceleration can help us if the motion of an object is influenced by external forces or not, or the object is in equilibrium with all the forces acted on it. So we examine the first type of the graph, which is the displacement type graph. So basically the number one, the graph shows the position of a dancer moving across a stage. Okay, this is the displacement time graph. Position is actually the displacement s. So before we going through the question here, let's see, let's examine, let's analyze the graph part by part first. So the first 5 seconds, it seems that the dancer doesn't change its position. So that means it's at rest. So this entire time period, the dancer is at rest because it doesn't change its position, thus doesn't change its displacement. But during the next 10 seconds until 15 seconds, 5 to 15, the dancer seems to change its position gradually, uniformly. So, increasing uniformly, sorry. So, it means that increasing uniformly the displacement, so it also means that it's at constant velocity. Okay. So this is increasing uniformly is the position, the displacement. So that means it's constant velocity. So how we know that it's a constant velocity or not the other type of velocity? Because it's represented by the gradient of the displacement time graph. So if we see here, the gradient or the line is a straight line, so it's a linear type of graph, and it's positive, rise to the positive direction, in a positive direction. So it has a positive gradient, and also the gradient is constant everywhere along this line. So that means that it has a constant positive velocity. Okay, so we move on to the next 5 seconds, 15 to 20. It seems like the dancer doesn't change its her position again, so it's at rest. And finally, the last 5 seconds, the dancer move towards the origin. So we have a negative gradient, thus negative constant velocity. Okay, but the magnitude of the gradient compared to the previous one, this one is steeper, thus has a larger velocity, even though it's negative. The negative is just the sign of direction. sign of direction. Basically, the dancer is moving towards the origin. So here is the origin, this line here. Okay, now we're ready to answer some of the question. A, what was the starting position of the dancer? So the starting position is actually at 4 meter. At 4 meter from origin. From, so let me clear a little bit here. So basically, we just look at the graph and interpret it from origin. Okay. B, in which of the sections A through D is the dancer at rest? So we look at the dancer at rest when A and C. A and C sections. Okay, the rest of the section, the dancer actually moves with a velocity. In which of the sections is the dancer moving in a positive direction? Of course, the positive direction is the positive velocity. So this is the only part that the dancer is moving in the positive direction. B. In which of the section is the dancer moving with a negative velocity, which is, we already discussed it before. This is D. Okay, so far so good because it's quite direct question. Now we move on to the next part where we probably have some kind of calculation that we need to do. So the following information relates to the questions 2 to 6. Okay, the graph represents the straight line motion of a radio controlled toy car RC car. Okay. So before we move on to the question one by one, so let's check first our understanding about the graph. So basically it's a position time graph, or other name is displacement time graph. Okay, so it starts from origin and moving towards the positive direction. So we have constant velocity, positive direction. Okay, and then it doesn't change its position here, so it's at rest, zero velocity. Okay, and then it seems like it moved back towards the origin. So we have constant velocity, but in the negative direction. And then after it passes the origin, it still continues its movement towards the opposite direction. So the whole line here is still in constant velocity, negative direction. But then when it reached 2 meters behind the origin, it stopped. It doesn't change its position, so it rests again. Zero velocity. Okay, so number 2, describe the motion of the car. So we can say that for the first 2 seconds, the car moves with a constant positive velocity, and then it at rest for 2 seconds until 4 seconds. And then after 4 seconds, it moves with constant negative velocity towards the origin and passes the origin until 2 meters after it, behind the origin. And then for the next 1 second, it stay at rest. Okay. So that's the motion of the car. We describe it in terms of velocity and the gradient. So which is basically the velocity. What was the position of the car after 2 seconds? So what was the position of the car after 2 seconds, which is basically at rest and at 8 meters from origin. 8 meters from origin, or positive 8. So after 4 seconds, towards origin. Moving towards origin, 2 meters behind origin. 2 meters behind origin, 6 seconds. 6 seconds. So we cannot say it's 2 meters behind origin then. We can say that we just take the position at 4. Now it's become more clearer. Still at 8 meters from origin. 6 seconds is 4 meters from origin. And 10 seconds is at 2 meters behind origin or opposite. Okay. When did the car return to its starting point at 8 seconds? 8 seconds. So we see that the car passes the origin before it continues its movement towards opposite direction. So what was the velocity of the car during the first 2 seconds? So in order to calculate the velocity, since it's the position time graph, the gradient is the velocity. So we need to find the gradient at 2 seconds during the first 2 seconds. So the formula for gradient, y2 minus y1, x2 minus x1. So y2 is 8 cm minus 0 divided by 2 seconds. So we get 4 cm as negative 1. So that's the A question. B, after 3 seconds. So after 3 seconds, it at rest. So we don't need to explicitly show our calculation here. We just say that 0 cm as negative 1. C, from 4 seconds to 8 seconds. So 4 to 8. So we need to calculate V equal to the final velocity is 0. Final velocity. Final displacement, sorry. Final displacement is 0. And then minus the initial. Initial is 8 cm. And then how long? 8 minus 4. 8 seconds minus 4 seconds. So we get negative 8 divided by 4. We got negative 2. Negative 2 cm as negative 1. So the negative sign here shows that it moved in the opposite direction. So basically it's true because we see that the car actually moving towards the origin where it comes from and then passes through it. Okay, D, at 8 seconds. Okay, at 8 seconds, since it's the same line, which has the same gradient, so it still has the same velocity. Cm as negative 1. So from 8 to 9, also the same straight line. So it has the same gradient and same velocity. Okay, so far so good. 6. During its 10-second motion, what was the car's distance travel? So this is a very good question. We just need to add up all the distances that the car has traveled from the start. So the first 2 seconds, it moved 8 meters. Regardless of the direction, actually, we don't need the negative sign here. We just add up the magnitude because distance is a scalar quantity. So 8 meters and then doesn't move, so doesn't have any distances. And then we move how many? 8 plus 2. 8 plus 2, 10 meters. 8 meters to return to the origin, and then 2 meters extra opposite direction. And then at rest, so no count there. So actually the distance traveled is just 18 meters. How about the displacement? So the displacement is actually we compare to the initial position here, which is origin, and then the final position here. Final position here. And then we see that it's -2. -0, -2 -0, final minus initial. So -2 -0. So actually it's -2 meters. Okay, next. Okay, now we move on to our next type of graph, which is the velocity time graph. The velocity time graph is very important because it can give us two information. The first one, the gradient. The gradient is actually acceleration. And also the area under the graph. It can give us the information about displacement. Okay. So other than we can describe the velocity itself, the movement, also we can describe the acceleration based on the gradient, and also we can know the displacement due to the area under the graph. Okay, let's see. The following information relates to question 9 to 11. The following graph shows the motion of a dog running along a footpath. So it's a dog. In this problem, north is considered to be positive. Okay, good. So before we move on to the question, like always, we just need to check each part of the graph, each section of the graph. So for the A section, it's velocity. So this is the velocity time graph. So its velocity doesn't change. So it's moving in uniform velocity or constant velocity. Constant velocity doesn't change, so it has zero acceleration because the gradient is zero. So now the velocity is increasing uniformly, increasing uniformly, increasing uniformly. So it has a constant gradient towards the positive direction, so it has positive acceleration, constant positive constant acceleration. C is moving in the opposite direction, so it has decreasing. It's not moving in the opposite direction, sorry. It's decreasing velocity uniformly. So it has a negative constant gradient. So it's slowing down basically. Before it comes to stop at D, at rest. Here you come at rest because the velocity is zero and also the acceleration also zero. E, now it moves in opposite direction because the velocity is negative, and then increasing uniform velocity. Uniformly velocity. So the acceleration is still negative, but the velocity actually increasing. Yeah. And then stay at rest, not at rest, constant velocity. Constant or uniform velocity. So zero gradient, zero acceleration. Okay, so number 9, describe the motion of the dot during this section of the graph. So we already discussed about this answer before we attempt to number 9, but let's repeat. A, the dot move with constant or uniform velocity, zero acceleration. B, increasing velocity uniformly or positive acceleration, positive constant acceleration. C, the dot move with decreasing uniformly velocity or negative constant acceleration or negative constant deceleration. D, the dot at rest doesn't move or still have zero acceleration. E, the dot moving in the opposite direction with increasing uniform velocity and negative acceleration. F, the dot moving at uniform velocity, which is zero acceleration. Okay, so we settle number 9. Number 10. Calculate the displacement of the dot after 2 seconds. Okay, after 2 seconds, so basically it's just the area under the graph. So the area actually is a rectangle with height 1 and then base 2, 0, 2. So area, which is S equal to, S is the displacement, 2 times 1, 2 meters. So this A. B, 7 seconds here. So we have a little bit complicated shape here. So what we're gonna do, we can separate it into two shapes. So one is trapezium A, and then the other one is triangle. So this is 2, 4, 7, height is 3, and then this is 1. So let's calculate area A first, the trapezium. 1/2 times A plus B, the parallel side, which is this side and this side. 1 plus 3. And then the other side, which is 4 minus 2. 2. We got 4 times 2, 8. 8 divided by 2 is 4 meters. So the next area is the triangle, which is quite easy. The base, 7 minus 4 is 3. And the height, 3. So 9 over 2, 4.5. So the total is 8.5 meters. Okay. C, 10 seconds. After 10 seconds. Okay, so basically, okay, so this is not the correct answer because it says after 7 seconds, not between 2 to 7. That means that we have to add the displacement before. So it basically becomes 10.5. We have to add the displacement before it. So see, also the same procedure, we have to add the displacement before and then calculate the area. So the basically has the inverted trapezium shape, 8 to 10, and then negative 1. So we have to take count the negative sign here. So area as 1/2 the parallel side, which is this 2. So 10 minus 8 is 2 plus, this is 9 actually. 9. So 10 minus 9 is 1. And then the negative 1 height. So 2 plus 1 is 3. 3 times negative 1, negative 3. Negative 3 divided by 2 is negative 1.5. So the total displacement we have to add before, basically it's just 10.5 meters plus minus 1.5 meters is actually 10.5 meters minus 1.5 meters. It becomes 9.0 meters. Positive. Okay, so far so good. Number 11, plot a position time graph of the dog's motion. Okay, basically we already calculated all the parts of the displacement for the dog. So we just need to plot. So S M P so second, yes. S. So basically you make sure that you sketch the graph, plot the graph using a ruler. Make it clearer and near. So during how many seconds here? We have 2, 7, 10. 2, 7 around here, and then here. You just need these 3 points. It doesn't need to make it very detailed here. During 2 seconds, it moved 2 meters. So we got 2 here. And then after 7, it moved to 10.5. Make it the highest. 10.5. Sorry. And then after 10 become 9, a little bit low. 9 here. So let's make it more visible. So we can just continue the line. Sorry, then it's more pretty. It actually curved, but we can make it approximately. Yeah, that's good. That's good enough. Okay, let's move on to the next question. Okay, number 13. The velocity time graphs for a bus and a bicycle. So we have two objects here. Traveling along the same straight stretch of road as shown below. The bus is initially at rest and starts moving as the bicycle passes it. Okay. So basically the bicycle is moving at constant velocity, moving at uniform or constant velocity, doesn't change its velocity throughout the time, throughout the journey, but the bus actually starting from at rest and then increasing its velocity uniformly here. So increasing uniformly the velocity, positive direction, positive acceleration, and then also increasing uniformly here. Positive direction, positive acceleration, and moving at uniform velocity for the rest of the journey. So zero acceleration, same with the bicycle, so zero acceleration. So A, calculate the initial acceleration of the bus. So initial acceleration, we assume it's just for 4 seconds. So calculate the gradient. Acceleration, y2 is 8 cm, oh not cm, meters. So meters as -1 minus 0 divided by 4 seconds. So 8 divided by 4 is 2 meters, -2. So positive direction, good. Positive acceleration. B, when does the bus first start gaining ground on the bicycle? When does the bus first start gaining ground on the bicycle? So we can say that gaining ground means that same position as the bicycle. So at 4 seconds. See, at what time does the bus overtake the bicycle? So we can say that it during at each second until 24 seconds. Overtake means that it passes through it successfully moving in front of the bicycle faster than the bicycle. D. How far has the bicycle traveled before bus catches it? So it means that we have to find the area under the graph for this section here before the bus overtake it. So the area is actually not a square, a rectangle. 8 height and 4 base. So 4 times 8 become 32 meters. Okay. What is the average velocity of the bus during the first 8 seconds? So average velocity is equal to total displacement divided by total time. So we have to find the displacement first for the first 8 seconds. So basically, it has the shape like this. It has a triangle and a trapezium, so we can split it into two areas. 0, 4, 8, and then the height is 8, 12. Okay, so the area for A is a triangle. 4 base, 8 height. So 32 divided by 2 is 12 meters. Well, not 12, 16. Sorry, 16 meters. B is the trapezium. So the parallel side here and here, 8 and 12. And then the rest of the side is 8 minus 4 is 4. So 20 times 4, 80. 80 divided by 2 is 40. So the total displacement is 56 meters. So we can calculate the average velocity. 56 meters divided by 8 seconds. So we get 9, I think. Oh, not 9, 7. 7 meters per second. Okay, good. I think that's all for today. Hopefully that you can master it, the concept behind the motion of the graph. We didn't discuss about the acceleration time graph because it contains the very least information that we can find out. But doesn't mean that it's not important. So make sure that you study about the acceleration time graph also. But the most important thing here is the velocity time graph because it contains a lot of information. Some of the information is relating to the acceleration and some of the information also relating to the displacement. So make sure that you remember that when we have the displacement time graph, the gradient is actually the velocity. Okay, but for the velocity time graph, it has two information, extra information. The gradient is the acceleration. Area under the graph is the displacement. Okay, that's all from me. Hope to see you guys soon. Thank you.